The B-52 first flew before the microchip existed, before color television reached most living rooms, before anyone had walked on the moon, before the engineers who maintain it today were born. Since then, America has designed, built, and flown a series of far more advanced bombers, faster ones, stealthier ones, aircraft built with computers, composites, and technology that did not exist when the B-52's wings were drawn with slide rules. Billions of dollars have gone into replacing it. Yet several of those replacements have already been retired, phased out, or wound down. The aircraft they were built to replace is still flying, still being upgraded, still scheduled to operate decades from now. So why can't America replace a bomber designed more than 70 years ago? The answer is not that engineers failed to build something better. It's that nobody has been able to build something that does everything this aircraft does at the same time. Chapter 1. The plane that refused to become obsolete. Most people assume the answer is obvious. Old airplane, outdated technology. Replacing it should be simple. The engineering reality is almost the exact opposite. When Boeing's engineers designed the airframe in the early 1950s, they were working without computer-aided design, without finite element analysis, and without any reliable way to calculate the stresses the aircraft would actually encounter. So they did the only responsible thing available to them. They overbuilt everything. Wings, fuselage, and internal structure were given enormous safety margins because the engineers could not precisely quantify the loads and refused to guess narrowly. The result was an airframe far stronger than its own mission required, with load cycles far beyond what anyone expected it to fly. They also left space. Systems were not packed into every available cubic inch. Access panels were generous. Wiring runs were reachable. Nothing was optimized to the last gram. By the standards of modern aerospace design, all of that looks like inefficiency. It turned out to be the single most valuable engineering decision in the aircraft's history. Because an airframe with unused structural margin and unused internal volume is an airframe that can absorb change. New systems can be added, heavier equipment can be carried, entire subsystems can be swapped out without the structure objecting. Most aircraft are designed precisely for one era of requirements. Optimized aircraft cannot flex because there is nothing left to give. This one could, and that mattered enormously because the requirements were about to start moving. Chapter 2. Every replacement solved. The wrong problem. Over the following decades, engineers repeatedly set out to build a successor. Each program began by identifying what the older aircraft did poorly, then engineering a solution. Each one worked, and each one created a consequence nobody had fully priced in. One approach chased speed and low-altitude penetration, with variable geometry wings that could sweep back for high-speed dashes and forward for efficient cruise. It solved the survivability problem of flying predictably at high altitude. But swing wings mean hinges, pivots, actuators, and ceiling surfaces carrying enormous structural loads. Complexity went up, maintenance hours went up, and the fuel required for high-speed flight cut into the one quality nobody wanted to lose: endurance. Engineers had solved one problem, only to hand themselves another. A later approach chased detection instead, shaped the aircraft so radar energy scatters away rather than returning. Coat the surfaces in materials that absorb rather than reflect. It worked extraordinarily well. It also produced an aircraft whose exterior had to be maintained to near laboratory tolerances in climate-controlled hangars by specialists after almost every flight. Cost per aircraft rose so steeply that the fleet was cut to a fraction of what was planned. A stealth aircraft you can only afford in small numbers and can only turn around slowly solves detection while creating a new problem: availability. This is the pattern that repeats across 70 years. Replacing one capability was straightforward. Speed could be improved, stealth could be achieved, avionics could be advanced. Replacing all of them simultaneously in one airframe at a cost that allows a large fleet is a completely different engineering problem. And the target the engineers were aiming at was not standing still. Chapter 3. The mission kept changing. Here is where the real antagonist finally appears. The hardest thing to engineer around was never the aircraft. It was the fact that the job kept being redefined. The original requirement was narrow and specific. Carry a heavy load in intercontinental distance at high altitude as a deterrent. That is a clean engineering specification. You can optimize an airframe for it. Then, the requirement changed. Precision-guided weapons arrived, which meant an aircraft now needed targeting systems, data interfaces, and internal wiring nobody had planned for. Standoff weapons arrived, which meant the aircraft no longer had to survive over a defended target at all. It had to loiter far away and release from distance. That inverted the value of stealth and speed and increased the value of endurance and payload volume. Digital networking arrived, which meant an aircraft was expected to receive and share information in flight, functioning as a node rather than an isolated platform. Each shift changed the specification an aircraft was supposed to be optimized for, and that is where highly optimized designs began to fail in a way nobody had predicted. A replacement program typically takes 15 to 20 years from concept to service. If the mission requirements change meaningfully every decade, an optimized aircraft can arrive already tuned for a problem that has moved on. The engineering target was moving faster than aircraft development itself, which meant the most valuable property an aircraft could have was not speed or stealth or efficiency. It was slack. Chapter 4. Bigger technology created bigger problems. Modern aerospace engineering solved problems the 1950s could not touch. Composite structures replaced metal, cutting weight while increasing strength. Fly-by-wire replaced mechanical linkages. Sensors and processing power transformed what a crew could see. Radar cross-sections shrank by orders of magnitude. Every one of these was a genuine engineering achievement, and collectively, they made aircraft dramatically harder to own. Low observable surfaces require specialized coatings, controlled environments, and inspection regimes measured in maintenance hours per flight hour. Composite structures are superb until they are damaged, at which point repair requires specialists and equipment that a simple metal patch never did. Deeply integrated avionics mean that changing one system can require requalifying several others. Complexity did not just raise the purchase price, it raised the cost of every hour flown, every repair made, and every upgrade attempted for the rest of the aircraft's life. This is the irony at the center of the entire mystery. The more capable engineers made each replacement, the smaller and more expensive the resulting fleet became. And a small, expensive, difficult-to-maintain fleet cannot do the one thing the older aircraft did without effort: show up in numbers, repeatedly, cheaply, for decades. Technology had become the problem. Meanwhile, something was quietly happening to the aircraft everyone assumed was obsolete. Chapter 5. The airplane engineers keep rebuilding. Here is the part that reframes everything. The B-52 flying today is not a 70-year-old aircraft in any meaningful engineering sense. It is a 70-year-old airframe carrying almost entirely modern systems. Engineers have stripped out analog instrument panels built around mechanical gauges and rebuilt the flight deck around large multifunction digital displays, consolidating navigation, sensor, and targeting information into unified screens. They have installed a digital communications backbone, allowing the aircraft to receive and share information in flight, connecting it to systems that did not exist when it was designed. They have replaced mechanically scanned radar with electronically scanned array systems derived from technology developed for modern fighters, steering the beam electronically with no moving part. They have replaced mechanically scanned radar with electronically scanned array systems derived from technology developed for modern fighters, steering the beam electronically with no moving parts. They are replacing engines that have run for more than 6 decades with modern commercial-derived turbofans, improving fuel efficiency, extending range, cutting maintenance demand, and generating far more electrical power for everything else being added. None of it has been easy. Engine integration has run into inlet design problems that caused real delays. Radar programs have struggled with integration, parts supply, and software. The structure itself now requires constant inspection for fatigue and corrosion after decades of accumulated load cycles. But every one of those upgrades was only possible for one reason. The airframe had room, structural margin to accept heavier systems, physical volume to route new wiring, accessibility to reach what needed replacing, electrical headroom the new engines could feed. The over-engineering that looked wasteful in 1952 became the foundation that let engineers rebuild the aircraft repeatedly for for 70 years. The aircraft is old, its engineering is not. So the mystery finally resolves, and the answer is not the one most people expect. Engineers never failed to build a better bomber. They built faster ones, stealthier ones, and far more sophisticated ones, and every one of those aircraft did its specific job better than the design it was meant to replace. What they could not build was one aircraft that solved every problem this one still solves simultaneously, at a cost that allows enough of them to exist. Range, payload, availability, affordability, adaptability. Any of those can be engineered brilliantly on its own. Together, they remain one of the hardest optimization problems in aerospace, and that is the deeper lesson buried in this story. The most durable engineering decision in the entire history of this aircraft was not a technology. It was the choice to leave margin, to build something strong enough and open enough that future engineers, working on problems nobody had imagined, would still have room to work. The aircraft did not survive because it was perfect. It survived because it was never fully optimized, and that turned out to be the one advantage no replacement could design in after the fact.